Okay, today we will do the first revision tutorial. In this tutorial, we're gonna have four questions. The first one gonna be on the bearing capacity of the pile groups without the settlement calculations. And the second one will be the pile raft foundations. And the third one and the fourth one will be regard the laterally loaded piles. We have already done these questions in the previous tutorials. For example, the first one, we have done it in tutorial number 4. And question number 2, we have done it in tutorial number 5. And questions 3 and 4, we have done them in the last two tutorials, 6 and 7. So we're gonna start with the first questions. Question number 1. In these questions, it's proposed to use a pile foundation to support a new power generation planet. The foundation is expected to support a total unfactored vertical load, dead load of 5 meganewton, including the pile cap. So here we have the first working load, which is 5 meganewton. The foundation will also support a live load of 1 meganewton. So that's the second working load. And to find out the total working load, it's gonna be 5 plus 1, so it's gonna be 6 meganewton. Due to the emergency load of the equipment, that's the extra 1 meganewton, the proposed piles are 50 meter long. This is the length of the piles, proposed piles, with a diameter of 406 millimeter or 0.406 meter. The pile wall thickness will be 12.7 millimeter. This is the shell thickness of the pile. The piles will be driven in silty clay layers whose properties are given in table 1. Here we have the properties of the silty clay layer. That's the thickness of the first or the top silty clay layer is 50 meter, which is exactly the same as the length of the pile, and that will rest on the bedrock. So it will be in bearing piles. The pile wall thickness will be, so we have done from that, and will be founded on the tail bedrock. The recommended pile spacings is 5 to 6 times the pile diameter. So this is the spacing to diameter ratio, 5 to 6. The elastic modulus of the pile is 200 gigapascals, and its cross-sectional area is 15,700 millimeter square. The allowable vertical settlements is 25 millimeter. The equipment layout requires that the dimension of the pile cap be 5 meter times 3 meter. This is the dimension of the pile cap, which gonna carry the load. A load test carried out on a single pile gave a deformation of 15 millimeter per 500 kilonewton. That will be required for the settlement calculations here. So we need here to determine the ultimate pile capacity of a single pile. And we need to design the pile group using a total overall factor of safety of 3. We have been given here the properties of the soil on the site area, here. Okay, so we're gonna go to the answer here. That's from week number 4. Okay, so as you can see in this questions, we do have the working load on the pile group. It's gonna be 5 meganewton plus 1 meganewton, so it's gonna be in total 6 meganewtons. We have the diameter of the pile is 0.406 meter or 406 millimeter. We have the length of the pile as 50 meter, and it's in bearing because it's resting on the bedrock. The spacing to diameter ratio is 5 to 6. We will not need the modulus of elasticity of the soil and the pile because that will be required for the settlement calculations here. The cross-sectional area of the pile is given as 0.0157 meter square, and how to calculate that. It's from the external diameter and the internal diameter. We only need the shell area because that's where the end bearing will be resting or will be calculated, because we need the cross-sectional area of the pile. So we only need the actual area of the pile material, which is obviously the shell area here, And to calculate that, we need to apply this formula, which is the external, to consider the external circle and the internal circle, and then to work out what's the area of the shell area within the shell area here. And that's how we calculate it. And then to find the first questions here, we need to find what's the ultimate pile capacity of a single pile. So for the single pile, we need to apply this formula, which is PSU plus PPU, which is the shaft resistance, or the shaft bearing capacity, or the bearing capacity due to the shaft resistance, and the bearing capacity due to the end bearing or the resistance at the end bearing area. So here, the shaft, the bearing capacity due to the shaft resistance will be equivalent to the Fs multiplied by As. Fs is the shaft resistance, and that's multiplied by the shaft area. So the shaft area here is by dl, which is the perimeter here, which is 0.406. That's multiplied by the length of the pile, pi d multiplied by the length of the pile. So that's the perimeter area, or the shaft area, which is the perimeter multiplied by the length of the pile, and that's multiplied by the alpha multiplied by Cu. And to find the value of alpha, it's a function of the Cu value. So we need to use this this chart here, which gives the reduction factor alpha as a function of the undrained shear strength. We have been given that the undrained shear strength here as for the soil layer as 50 kilopascal. So we need to take that 50 kilopascal and to draw a vertical line until we cross the curve here, and to read the value of alpha. And the value of alpha will be around 0.9. So we take the value of alpha as 0.9, and we put the value of undrained shear strength as 50. So that's the bearing capacity due to the shaft resistance. And then we need to work out the bearing capacity due to the resistance due to the end bearing value. And that will be the undrained shear strength multiplied by the NC factor. That's multiplied by the cross-sectional area of the pile. And the cross-sectional area of the pile, we have already worked it out here. So we need to multiply this value by this factor, which is FB factor, which is for the clay soil, is the undrained shear strength multiplied by the NC factor. NC factor is a function of L over D. So we need to find what's the length over diameter ratio. So the length over diameter ratio, we take it to this chart, and then we draw a vertical line until we cross either the continuous or the circle or square. That's depending on the cross-sectional area of the pile. In our case, we have a circle, so we're gonna use the upper curve here. So once we find what's the value of the length of the pile over the diameter of the pile, we draw a vertical line until we cross the value here. So anything, as you can see, more than 4 will give us NC value equal to 9. So we have here the length of the pile is 50 meter. That's the length of the pile, and the diameter of the pile is 0.406. So if we divide 50 by 0.406, obviously we're gonna get a value much larger than 4. So that will give us NC value equivalent to 9. So if we put everything back into the formula, we use here the Cu value, but the Cu value is the one for the bottom soil, here, because we have two soil here, and we know that the end bearing, or the tip of the pile, is resting on the bedrock material. So we need to use for the end bearing resistance formula, we need to use the underlying shear strength of the second soil here. So that's 400. So that's what we put here. 400 multiplied by the NC factor multiplied by the cross-sectional area of the pile, and that will give us 2.93 mega Newton. So that's the first questions, which is determining the ultimate pile capacity of the single pile. We just need to apply this formula, which is the shaft resistance and the end bearing resistance. The shaft resistance within the soil, within the clay soil, is given by this formula, which is the perimeter area or the shaft area multiplied by this factor alpha Cu, and the end bearing resistance is in the clay soil is given by the underlying shear strength multiplied by the NC factor multiplied by the cross-sectional area of the pile, and that will give us 2.93 mega Newton. Now we need to work out the second questions, which is design the pile group using a total overall factor of safety of 3. So to design the pile group, as we can see, we have in the first question, we have designed the single pile. But obviously, the single pile, as we can see, only carry a 9.93. This is the ultimate bearing capacity of the single pile, 2.93 mega Newton. But we have a working load of around 6 mega Newton. So obviously, the single pile will not able to carry the 6 mega Newton, will not be enough to carry the 6 mega Newton. So obviously, we need a set of piles within this area, within the 3 by 5 meter area. So that's the requirement in the second questions. We need to find out the layout of the pile, the number of the pile, which is required to carry out the 6 mega Newton safely, given that the factor of safety is 3. So we need that requirement. We need the number of the piles and the layout of the piles. The layout of the pile, which is centered to center, the spacings, the distribution of the pile within the 5 meter by 3 meter pile cap. So to do so, we need firstly to find the approximate number of the pile, the approximate number of the piles. So to do so, we need to take the factor of safety and then to find what's the working load by each pile, taken by each pile. So to find out this value, we need to divide the 2.93 by 3, which is the factor of safety. So this is the safe working load. This is the maximum working load the single pile can carry for a factor of safety equal to 3. So as we can see here, we got this number, 0.977 mega newtons, and we know that the pile group has 6 mega Newton. So we need to carry 6 mega Newton. So this is the total working load. Each pile can carry a working load of 0.977. So we need to divide the total working load by the working load carried by the single pile, and that will give us approximately 6 piles. And then we need to lay out these piles within the 3 meter by 5 meter. And we need to remember that the spacing to diameter is 5 to 6. So we can take 5, we can take 6. We will try with the first one, which is 5, the spacing to diameter ratio, because we need to find out what's the value of spacing center to center. Given this design value as spacing to diameter is 5, we know that the diameter value is fixed, which is 0.406 meter. And by doing so, we can work out the value of spacings is equivalent to the 5, which is the ratio of spacing to diameter, multiplied by the diameter of the pile, and that will give us 2.03 meter. This is the spacings of between the piles center to center. And then we can work out, this is the layout. The layout from this point to this point, we need at least a dimension here, 2.03 plus 0.406. So that will give us 2.436. And on in the long dimensions, we're going to have 2.036, 2.03 between these two piles and another 2.03 between these two piles, and we need the diameter of the pile to be added to this value. That will give us 4.47 meter. So we can see if we compare these two numbers, 4.47 and 2.436, with the available pile cap, 3 meter and 5 meter, we know that they are approximates and they are less. So we need at least 4.47, and we have 5 meter allowed. We need 2.436, and we have allowed 3 meter. So as we can see, we met the requirements. So the pile cap size is satisfactory for the layout of the 6 piles here. Then we need to check what's the ultimate bearing capacity using the single pile approach. We have already determined what's the ultimate bearing capacity of the single pile, which is 2.93 here. We have already determined this value. We need now to determine for the pile group, but using the single pile failure scenario, assuming that each pile will fail by separately, individually and independently of the adjacent piles, and that will give us the number of the pile 6, which we have determined this step here. 6 multiplied by the ultimate bearing capacity of the single pile, that will give us the ultimate bearing capacity of the pile group using the single pile failure scenario, and that will give us 17.58 meganewton. Now we need to check for the block approach, assuming that the pile here will fail as a block, not independently, but will fail as a block. To do so, we need to apply the same formula as this formula here, but what we need to change, we need to change here the shaft area, because the shaft area here is for single pile, so we need to change that to the shaft area for the pile group, for the block of the pile, which is 4.47 plus 2.436, and that's double this amount. We'll get the perimeter of this area, and if we multiply this by the length of the pile, we'll get the shaft area. So we need to apply this formula here. The same value for alpha and CU. Alpha will be 9, CU will be 50, and the perimeter area here is 4.47 plus 2.436, double this amount, and that's multiplied by the 50, which is the length of the pile. That will give us the shaft resistance for the block of the piles, and then we need to find what's the bearing capacity, the end bearing capacity, or the resistance at the end bearing area, and that will be CU and C. CU will be the same for 100 for the bedrock multiplied by NC. We need to check what's the value of NC, because now we're gonna have a new length over diameter ratio, which is gonna be 50 divided by the largest dimension here, where that's gonna be 4.47, and that will give us obviously a value more than 4. If we go to this chart here, anything more than 4 will give us NC equivalent to 9. So no change in the value of NC as the single pile failure scenario. It's going to be the same as the block approach. And if we substituted all these values here, then we're going to get what's the ultimate bearing capacity for the block of the piles as 70.3 meganewtons. And we know that we need to take the minimum value between these two values, 17.58 and 70.3. We need to take the single pile failure scenario, the PU group from the single pile approach. So that's going to be 17.58. Then we need to divide this value, because this is the ultimate bearing capacity of the pile group, 17.58, by the available factor of safety, and that will give us 5.86 meganewton. Approximately this value is equivalent to the working load, which is 6 meganewton. So we can say that the 6 piles with the factor of safety 3 is satisfactory to carry the applied load, which is 6 meganewton. 6 meganewton here. Okay, so that's for the first questions, which is determining the ultimate pile capacity of the single pile and determine the pile group using a total overall factor of safety, which is equivalent to 3. We need to find what's the layout of the pile. We need to determine the ultimate bearing capacity of the pile group, and to find, to compare that with the factor of safety. obviously, and to find out if the working load at this particular configurations determined piles will be sufficient or satisfactory to carry out the required working load, which is 6 meganewton here. And that's what we have done in this analysis. In the second questions, we need to find out for the pile raft foundation problem given below. We have here the layout, we have the cross-sectional area as well, the elevations and the plan view. Construct the trilinear load displacement response using the Modulus and Davis approach. And the size of the flexible raft, we have here a flexible raft, which is 2.5 meter by 5 meter, the long dimension. The spacing between pile is 1.5 meter, that's center to center, 1.5 meter, another 1.5 meter. The design load acting on the raft is 5 meganewton. This is the working load, 5 meganewton. The diameter of each pile is 300 millimeter, and the length of each pile is 7.5 meter. A load test gave 50 millimeter settlement at 500 kilonewton. That's for the standalone pile. Boson ratio of the soil is 0.5, and the ion modulus of the soil is 40 megapascal. That's for the soil itself. We only have one soil here in the problem, and it's the same within the shaft and the end bearing area. Assuming that the ridge stratum lies far below the base of the piles, we need to calculate the settlement of the pile raft foundation. So this is a settlement calculation here. We have here the underhand shear strength of the soil, 75 kilopascal. The average reduction factor alpha is 0.4. We can find this value obviously from this chart here. For the 75, around somewhere here, that's 20, 40, 60, 80. So 75 will be somewhere here, and that will give us the reduction factor, approximately the reduction factor value. Okay, the average reduction factor is equivalent to 0.4. The settlement of the rectangular raft alone is given by this formula here. So what we need to do here, we need to find, according to the Modulus and Davis approach, so this approach, we need to separate the settlements as settlement due to the pile settlements and settlement due to the raft settlements. And then we work each settlement separately, and then we add them together at the end. So we need to find what's the settlement due to the pile and due to the raft, okay? So to do that for the pile, we need to find what's the load acting on the pile. And because it's a flexible, so for the flexible raft, we do have the settlement of the side piles will be different from the settlement of the center piles, of the piles on the center. So we're gonna have two different settlements within the pile group here. We're gonna have piles, we can give them the symbol A. That will be the side piles, this one and this one and this one and this one. And we have the piles within the center, we can give them the symbol B. So this one will be B and this one will be B. And then we can find what's the settlement on each of these piles. And we know that from the flexible raft approach, that the load acting on these piles are the same. So the load on pile A is the same as the load on the pile B. Okay, so to start on the solution here, firstly, we need to find out if the raft alone is sufficient to carry out the load. So the load here we have is 5 meganewton. We have a working load which is 5 meganewton. So the load carried by the capacity is the same. This is the formula for the shallow foundations, Mehrhof shallow foundations for the load carrying bearing capacity. If we apply this formula, obviously we only have a clay layer. So for the clay layer, we have the friction angle is equivalent to 0. So the bearing capacity factor in gamma NQ will be equivalent to 0. We only end up with NC value, which is 5.14. And if we apply that in here, that term will be cancelled, will be 0, and that term will be 0. So we're going to end up with this term here, CU NC. CU is equivalent to 75 and NC is equivalent to 5.14. That will give us what's the ultimate bearing capacity or the bearing capacity of the raft itself. That will be 385.5 kilopascals. And to find the ultimate bearing capacity here, the load carrying capacity, we need to multiply by the area, by the raft area, which is given as 2.5 by 5 meter. So we multiply the ultimate bearing capacity to find the load. The bearing capacity, we multiply the ultimate bearing capacity we obtained from the previous step, from the Meyerhof equations, by the available cross-section area of the raft. And that will give us approximately 4.82 mega Newton here. So this is the available load carrying bearing capacity. If we compare it with the working load here, which is 5 meganewton, because this raft is required to carry out 5 meganewton. And we can see that the factor of safety is not satisfactory. If we divide 4.82 by 5, we will get a factor of safety approximately equivalent to 1. So we know that the raft by itself is not sufficient to carry out the required working load 5 meganewton. And that's why we need to add the piles to this raft systems. So now we need to design for the pile. We need to know what's the ultimate bearing capacity of the single piles, and what's the carrying load, what's the load carried out by the pile groups by itself, and what's the load carried out by the raft itself. So to do the bearing capacity of the pile group, we need first to find using the single pile failure approach. So it's the same formula as the previous questions. We do have the ultimate bearing capacity of the single pile is equivalent to the end bearing resistance plus the shaft resistance here, or the bearing capacity due to the shaft resistance, and the bearing capacity due to the end bearing resistance. Because we only have a clay layer, so it's the same formula as previously. So it's gonna be FB multiplied by IB plus AS multiplied by FS. So we need just to substitute this value here. And obviously the value of CU is equivalent to 75. The value of NC, we can find it from this chart here. We can find it from this chart. After finding the value of L over B, the length of the pile over the diameter of the pile, anything over 4 will give us NC value is equivalent to 9. And obviously we got a value of 25 as length over diameter ratio, and that will give us NC equivalent to 9 according to the previous chart. So we put this value here, and then we need to multiply this number by the cross-section area of the pile. We got here diameter of the pile is 0.3. That will give us what's the cross-section area of the pile, and then we multiply by, we add this number to the bearing capacity due to the shaft resistance, and that's equivalent to the shaft area here, which is by D multiplied by the length of the pile, by D is 0.3, and the length of the pile is 7.5 meter, and the reduction factor is given as alpha as 0.4, and that's multiplied by the CU value, which is 75. And that will give us the ultimate bearing capacity of the single pile, which is 259.771 kilonewton. For the pile group using the single pile failure scenario, we need to multiply by the available number of pile, which is 6, and that will give us 1.56 meganewton. Now we need to check this value against the block failure approach. In the block failure approach, what's gonna be different is the shaft area and the cross-sectional area of the block of the piles. And obviously we need to recheck the value of NC because we need the value of NC here, and we know the value of NC is dependent on the length over diameter ratio. So we need now to check the new diameter, because now we're gonna have a new diameter here. We need to find what's the layout of the pile here, taking that, knowing that the spacings, diameter to diameter is 1.5 meter. So we have here the spacing between the adjacent pile as 1.5 meter by 1.5 meter, and that will be added to the diameter of the pile. So in this direction, we're gonna have 3.3 meter, and in that direction, we're gonna have 1.8 meter, because 1.5 plus 0.3, that will give us 1.8 meter in this direction and 3.3 meter in that directions. So that's what we end up with here. So the block cross-section